So good day, everyone. Andrew De Silva here, and welcome back again to our little series on the circulatory system. Today, we're going to be looking at 3 learning outcomes from the CXC Human and Social Biology syllabus. Those are learning outcome 3.3, which asks us to relate the structure of the heart, the structures of the heart to their functions. 3.4, describe the structure and function of the heart. The explanatory note there being the role of heart as a double pump. We're going to skip learning outcome 3.5 and go to learning outcome 3.6, which asks us to describe the structure and function of the circulatory system. The explanatory note there being pulmonary versus systemic circulation. All right, learning outcome 3.5, which we're going to leave for a later class, deals with diastole and systole. The next class we'll be dealing with that, and we're gonna lump that together with blood pressure and the pacemaker, the AS, the SA, sinoatrial node, and the AV node. All right, but today we're gonna deal with those 3 learning outcomes because they're very similar, and it'd be difficult to deal with one without touching on the other. So it makes sense that we lump these 3 learning outcomes together. All right, so if we turn our attention to my whiteboard here, we see my very crudely drawn diagram of the heart and basic double circulation diagram. All right, the first thing I would like us to look at and talk about is the fact that the heart, our human heart, has 4 chambers. There are other animals, other living things that have hearts whose heart contains 2 or even 3 chambers, but we as humans, our heart has 4 chambers. I've numbered them there: 1, 2, 3, 4. All right, so we have the top 2 here, our atria. The 2 top chambers are the right and left atria, and the 2 bottom chambers are the right and left ventricles. So we have 4 chambers, 2 right and left atria, and 2 right and left ventricles. All right, between them there are valves, and these valves, much like the valves in our veins, prevent against the backflow of blood. We want blood to be flowing in one direction through our heart, and the function of these valves is to do just that. So here, between the atria, the right atria and right ventricle, we have the tricuspid valve. Right here we have the tricuspid valve, allowing blood to move from the right atria to the right ventricle. We then have another valve right here that is one of the semi-lunar valves. That's the pulmonary valve, which allows blood to flow from the right ventricle to the pulmonary artery and then to the lungs. We have another valve here, or the bicuspid valve, also known as the mitral valve, which allows blood to flow from the left atria to the left ventricle. And we have another of the 2 semilunar valves, which is our aortic valve, which allows blood to flow from our left ventricle to our aorta. All right, so these are the valves that exist. Now these valves, they have tendons. The tendons are not shown in this diagram, but they have tendons which strengthen them and give them support, because we can't have them breaking down. We would have looked at the valves in our veins and what would happen if they would break down, that being varicose veins and other things. But in our heart, we can't afford for these valves to break down. So these valves are supported by tendons to prevent any of that breakdown. Because if that is to happen, then our blood won't be flowing through our body as efficiently, through our heart as efficiently, and thus through the rest of our body as efficiently. And that decreasing efficiency of blood flow will decrease supply of oxygen and nutrients to our cells, and we don't want that, because that will come with a host of adverse effects. So we don't really want that. So the tendons are there to support the valves. All right, this center line here is the septum. All right, that septum separates the left and the right parts of the heart. When we were babies, when we were in our mother's womb, there was a hole in the septum which allowed blood to flow from one side to the other, because we weren't breathing. We were in our mother's womb, so we weren't breathing. There was no need for the double circulation that we're going to look at just now. So the blood just flow through the heart in that way. When we are born and we start to breathe, then that hole would close up. All right. There are some persons who the hole never closes, and it would cause atrial septal defects. All right, that needs to be surgically dealt with. All right. I know that Chris Gayle, one of our famous sportsmen and cricketers in Jamaica in the Caribbean, he had a hole in the heart. I can't say if this is the kind of hole that he had in his heart, but holes in the heart are very serious things that need to be dealt with. I think he got surgery for that. All right. At this time, I want us to look at the direction of blood flow through the heart. All right. And I would have labeled the direction, shown the direction with these orange arrows. So the blood first enters the heart from the vena cava. All right, we have a superior and an inferior vena cava. The superior vena cava brings blood back from the head and neck back to the heart, and the inferior vena cava brings blood back from the rest of the body, our trunk, our legs, our arms, our digits. All right, and the vena cava feeds blood into the right atria. So the first chamber that blood gets to when it enters the heart is the right atria. Blood, it then flows down through the tricuspid valve to the right ventricle. The right ventricle pumps blood to the lungs via the pulmonary artery and through the semilunar pulmonary valve. Now, the pulmonary artery is an exception to the rule that all arteries pump oxygenated blood. In general, arteries pump blood that is rich in oxygen, oxygenated blood, but the pulmonary artery is an exception to that rule. The pulmonary artery is transporting blood that has just returned from the rest of the body, where the blood would have given up its oxygen to the cells for their use in respiration. So blood returning via the vena cava, and thus blood flowing through the pulmonary artery towards the lungs, is deoxygenated blood. When the blood gets to the lungs, via the process of gas exchange, exchanging carbon dioxide for oxygen, the blood will now be rich in oxygen. Therefore, blood flowing through the pulmonary vein is oxygen-rich blood, oxygenated blood. So that too is an exception to the rule that most veins carry deoxygenated blood. The pulmonary vein does not carry deoxygenated blood. It carries, however, oxygenated blood because it just got all that oxygen from the lungs. All right, and from the pulmonary artery, blood enters back into the heart via the left atria. From the left atria, it goes down to the left ventricle via the bicuspid valve, and the left ventricle then pumps blood out through to the rest of the body through the aorta. All right, that's the direction of blood flow. And in this explanation, we see the double pump action of the heart. All right, we have two circulations within our body. The first circulation is the pulmonary circulation, and that's where the heart pumps blood to the lungs and back. All right, the heart pumps blood to the lungs and back. That's our pulmonary circulation. And the second is our systemic circulation. That's where the heart pumps blood to the rest of the body and back. All right, that's our systemic circulation. All right, so we have our two circulations there. Something I like to look at as well is, if you notice these spaces here, that's the walls of the heart. Right, the heart is made up of cardiac muscle, very strong, resilient, tireless muscles that beat even from before we are born. All right, when we're a couple of weeks, 2, 3, 4 weeks old, our heart has already started to beat, and it stops beating when we die. So if we live to 100 years old, our heart has been beating for 100 years. That's some strong muscle. Our cardiac muscle is very strong. I wish my skeletal muscles were as strong and as resilient as my cardiac muscles. Now, the muscles, or these walls, have varying thicknesses. I would like us to recognize that the walls of the atria are thinner than the walls of the ventricles. That's because the atria only has to pump blood a short distance. The right atria pumps blood down to the right ventricle. The left atria pumps blood down to the left ventricle, a very short distance. So the muscular walls of the atria don't need to be thick. They don't have much work to do. The ventricular walls, however, have to be thicker. The muscles have to be thicker because they have more work to do. The right ventricle pumps blood to the lungs and back. The left ventricle pumps blood to the body and back. And because of that, the left ventricle has the thickest walls of the four chambers because it has more distance to pump blood. The right ventricle only has to pump blood to the lungs and back. The left ventricle has to pump blood all around the body from the crown of our head to the tip of our toes. That's a lot of distance to travel. So the walls of the left ventricle are thicker because it has more work to do. All right. So yes. So we in there. Um, hmm. Now, in case I forgot to do it. Now, the left ventricle is pumping blood out under very high pressure, and this blood is first hitting our aorta. Our aorta is the thickest, strongest blood vessel we have because it needs to be able to work under very high pressures. It needs to be able to sustain these high pressures. All right, so it has the thickest walls and it's the strongest of our blood vessels because we're really trying to avoid a condition that we call aortic dissection. Aortic dissection occurs when, for some reason, the aorta is damaged, whether from trauma or some other disease or reason, and the pressure in the aorta would force blood to split the layers of the aortic wall, causing hemorrhaging and bleeding. If this happens, you will die within seconds because the blood is under so much pressure, because the ventricles is squeezing so much. You will bleed out in a matter of seconds. So even if you're in the hospital, you will die, unless, of course, the doctor has you on the operating table and he has already cracked open your chest and is already looking at your heart. Short of that situation, if you have an aortic dissection, you will die. All right. So we have covered the three learning outcomes. I am now going to put up a little summary that you could look at, you could write down, put in your notebook, and then it's going to be followed by some questions that I would love if you can attempt. All right. So have a good day. See you guys in the next one.